Take any source of energy or influence in the universe and step away from it. The further you go, the weaker it gets. We see this clearly in this diagram of a single point charge. According to Coulomb's law, the electric field strength drops off as the square of the distance. Double your distance from the charge, and the field drops to 1/4 of its original strength. This inverse square law dictates our intuition for almost everything physical. Gravity, sound, and light all dilute as they spread outward into three-dimensional space. But relying on point charge logic creates a significant blind spot. It completely fails us when we stop looking at isolated dots and start analyzing continuous, macroscopic distributions of charge. Specifically, when we scale an object's dimensions up to infinity, the inverse square law stops applying entirely. Consider an idealized, infinitely large two-dimensional plane. Notice how the electric field vectors pointing away from this plane maintain the exact same length no matter how far out they extend. To understand why, we first define how much charge we are dealing with. Since the plane is infinite, we can't count individual electrons. Instead, we use surface charge density. We measure the amount of charge per unit of area, represented by the Greek letter sigma. Here is the paradox. The electric field generated by this infinite sheet does not weaken. If you move 1 meter away or 1,000,000 meters away, the force you feel is exactly the same. How can an electric field escape the inverse square law? Where does the distance variable go? We can prove exactly why distance becomes irrelevant here by applying Gauss's law. Before we touch the algebra, we have to restrict the geometry of our electric field. We do this by strictly enforcing the rules of symmetry. Let's pick a random point in space above our infinite sheet. We'll call it point P. The electric field at point P is the sum of the influence from every charge on the plane. Let's look at the field contributions from two symmetrical charges located on opposite sides of our sheet. We can break these two diagonal vectors down into their directional components, the parts pushing vertically and the parts pushing horizontally. Because the two starting points are perfectly symmetrical, their horizontal components act in exact opposition. They perfectly cancel each other out. Because the sheet extends infinitely in all directions, every single charge on the left has a perfect twin on the right. Every charge in front has a perfect twin behind it. Symmetry dictates that all horizontal lateral drift is mathematically annihilated. The total electric field has no choice but to point strictly perpendicular to the surface. Now that we know the field lines are perfectly straight and perpendicular, Gauss's law becomes the ideal tool to evaluate the field strength. Gauss's law requires us to imagine a closed, three-dimensional boundary. We use this boundary to measure the total electric flux, the amount of electric field piercing through it. For a flat plane, the optimal boundary is a rectangular parallelepiped, often called a Gaussian pillbox. We position it so it cuts straight through the charged sheet. We assign a cross-sectional area to the flat top and bottom end caps of our box, giving it the variable A. We design this specific shape because its flat walls intentionally exploit the geometry of our field. They either perfectly align with the vertical field vectors, or they perfectly ignore them. Electric flux is simply the measure of field lines piercing directly through a surface. Look closely at the 4 vertical sidewalls of our rectangular pillbox. Remember our symmetry proof. All electric field vectors point straight out from the plane, perfectly vertically. Because the field lines run parallel to the vertical sidewalls, they slide right past. They never cross the boundary. Therefore, the total electric flux passing through the vertical sides of the pillbox is exactly 0. We can mathematically ignore them. That leaves only the top and bottom end caps of our pillbox. Here, the perpendicular field lines hit the faces dead on, piercing straight through them at perfect 90-degree angles. We calculate flux for these faces by multiplying electric field strength, E, by area, A. The top face yields E times A, and the bottom face yields E times A. Added together, the total flux leaving the pillbox is 2EA. Now we solve the second half of Gauss's law, determining the exact amount of charge physically trapped inside our pillbox. Recall our starting parameter, the surface charge density, sigma. The pillbox bites out a specific chunk of the charged sheet. That chunk has an area of A. So the total enclosed charge is simply the density, sigma, multiplied by the area, A. We now have both halves of our equation. Gauss's law states that the total flux, 2EA, is equal to the enclosed charge, sigma times A, divided by the electrical constant, epsilon naught. Look at the variables. The area, A, exists on both sides of the equation. This allows us to algebraically cancel the area variable entirely. The size of our pillbox doesn't matter. Rearranging to solve for the electric field, we get E equals sigma divided by 2 epsilon naught. The variable for distance, r, has completely vanished from the formula. The math proves that the field generated by an infinite sheet is perfectly constant, no matter how far away you travel. In physical terms, if you held a charged sphere over this infinite plane and moved it upwards, the force pushing your hand would never weaken. Of course, in the physical universe, a truly infinite sheet of charge is impossible, but physicists and engineers use this exact formula constantly. It forms the operating logic behind parallel plate capacitors, which store energy in almost every electronic device you own. This works because of what happens near the middle of a finite plate. As you move outward toward the boundaries of a real object, the perfect symmetry breaks down, creating what we call edge effects. At the edges, the field lines begin to bow outward and diverge. Once the lines spread out, the field dilutes, and the inverse square law dictates the behavior once again. But as long as you are measuring near the center of a large charged surface, and the distance from the surface is small compared to the size of the plate, the infinite sheet approximation is highly accurate. In that specific space, distance simply does not matter.